Can you hear me okay? Can you hear me? I'm going to type in the chat here. Can you hear me? It might be. Can you hear me now? No. Just going through the obvious. Testing, testing. Can you hear me now? Can't hear anything. Charlotte, it's just me. Charlotte. Hey. Oh, Charlotte. Now, oh, there it says connecting to audio. Can you hear me now? Okay. I didn't see when you joined last time, I didn't see the connecting to audio. So something didn't work there. All right, let me get my iPad going here. And it might just be you and me tonight, so you kind of have a private session, so it'll go at your pace and with your questions and so forth. I didn't have too much that I was going to go through. I wanted to go through that additional problem from today. And I'll give you an opportunity to kind of practice and go through it. And then when you're ready to kind of go through the solution, if you didn't get the right answer, or if you did get the right answer, I'll still probably go through the solution since this is recorded. And then if you had any questions on kind of stuff from the homework, if you will, that I gave you over the weekend from the problems that we had from Friday's class. So while I'm getting set up on my iPad, actually, let me try. Can you try to say something? I want to see if I can hear you now.
Can you hear me now?
I can. Yeah, and before there wasn't anything with a microphone. There wasn't an option to mute you. So somehow I just think last time it didn't connect with the audio somehow. So we are good now. All right, so let me just get connected here. And I don't see us needing more than maybe I'm happy to stay here for as long as you want, but we can probably get done what we need to get done in an hour in terms of the stuff that's new. So one of the things I've mentioned to a few people who I've talked to about this is I think they're cautiously optimistic because they're like, I think I understand this. I see the pattern. And that's it. I mean, these are challenging problems, but if you sort of see the pattern with what's going on. And again, each time we move on here, we have like a little bit more that we're adding in terms of complexity to a problem. But if you've mastered that previous one, kind of going to the next level usually isn't a challenge. So let me start my iPad here. And we will, now, did you have a chance to, and it's fine if you didn't, did you have a chance to work on that additional problem from the end of class today? Or
I
not?
did, and I think I got the right answer, at least based on what you said the answer was in class. So
Okay, all right. So what I'll do then is I'm going to go through and just kind of go right to the solution, since usually what people do, I think, when they're watching this video later, is they have the ability to pause it and work on the problem, and then they might need to fast forward just until we see the solution. But if you feel like you've got the solution, we're going to move right away to that. So let's see, we don't need to do biochemistry. Let's do this guy. Okay, so the answer should have been 3.78. So we go ahead, and I might actually ask you to mute yourself because there's just background noise. I just don't want it to. Feel free, unmute yourself if we're having a conversation or if you've got questions, but it might be something that will keep muted so we don't have background noise interfering with the recording. Okay, so the answer is 3.78. This is really, really congested because when I worked out the solution for this problem, I put it all on one page. And just to review, when we did this problem in class, or we did the acid problem in class, I kind of broke it up into 2 slides so it wasn't so congested. But just reviewing for everybody from class, what we did is the first thing you always want to do is ask who's in solution and kind of write down all the players, all the pieces that are in solution. So we have this buffer. So we've got a weak acid and its conjugate base. And in the problem we did in class, we added H+, so we added acid. Now, what I'm highlighting here is going to be different from what we do when we return from Thanksgiving break, is we're assuming that any of the solution or any of the H+ that we added, we're not considering changing the volume. And that's a difference from what we're going to deal with when we come back from break, when we deal with titrations. So once you figure out who's in solution, you're going to ask 2 questions. The first question is, does chemistry happen with anything that I put in solution? And in this case, we are going to have our acid react with our buffer conjugate base. So we're going to have that H+ do chemistry here. So we wrote a chemistry equation. Chemistry equations have one-way arrows, and we write an ICF table. And then we figure out the number of moles that are left of our weak base and our, I should say, our conjugate base, and then our weak acid here. Because we need to do the next step with concentrations, we need to divide by the volume that they're contained in to get to concentrations. And so that's the part that's going to be different when we come back after break, is that we're going to have to figure out what that new volume is. In this case, we're assuming that what we added didn't change the volume, so we still had a liter. And then we went through and said, now that the dust is settled, we had our battle, we know who's left. We have a decreased concentration of our conjugate base army, and then an increased concentration of our weak acid army. Then we do an ICE table to say what is going to be the pH of that solution. So I think the ICE table way takes more time, but for people who are struggling with this, it's like, hey, I know how to do ICE tables. I know how to solve for X and all of that good stuff. So it'll always work. But again, if we know that we've got a situation where we have a weak acid and its conjugate base, or a weak base and its conjugate acid, we can use the Henderson-Hasselbalch equation. So I know that's a review for you. And you said you did get the correct answer from today's kind of assigned problem to work on outside of class. So let's go through that solution. And the reason I went through that there is I'm going to show you that this is essentially the exact same kind of steps that we're going to work through. The only thing that's different is now we're adding OH minus. Okay, so the next slide is going to be pretty busy, but I'm going to break it apart in pieces here. So again, starting up here, we're going to highlight that we're adding all of this to 1 liter of buffer. That's part of the problem prompt that wasn't necessarily written out here. So that needs to be part of the problem because that's how we get concentrations, is we have to say how many moles that volume is contained in. So what's the same from the previous problem is we have a weak acid and its conjugate base. So we have a buffer, but now we're adding OH minus, we're adding base. So the first thing that we're going to do is we're going to do chemistry. And now that we've added base, the chemistry that happens is with our weak acid army, not our base army. So here's the equation for what happens. So this is chemistry. So we're going to be writing an ICF table because we've got a one-way arrow. Just like we had H plus as our limiting reactant when we did our first problem, now we're going to have OH minus be our limiting reactant, highlighting we know that that's our limiting reactant because we have the fewest number of moles of it. So because that's our limiting reactant, this is going to be what propagates our change column. That's going to go away as a reactant in terms of number of moles, and it's going to be added as a product in terms of number of moles. So in this case, when we do battle with a base, we are going to have an increase of our base army and a sacrifice or a decrease of our weak acid army. Now we need to convert these into concentrations. These are going to be the same numbers mathematically because we know that we have 1 liter of buffer. Now that we know who's in solution after the dust has settled, we have to figure out what is the pH of that solution. So again, we can use an ice table. Okay, so ice table, and what's different with ice tables right now than anything we've seen before, I didn't highlight this when we were running through our problem that we did in class, is we are going to have multiple species in the initial row. Okay, now as we're going to see, it really doesn't matter because we still have something that's a 0. So we know that this equilibrium is going to shift to the right. Highlighting when I write my equilibria for doing these problems, I like to write them as acid equilibria if I'm dealing with a weak acid and its conjugate base. The reason I like to do that is because acid equilibria are going to give me H plus as my X. It's easy to calculate pH from that. I also know that if I'm working with a weak acid and its conjugate base, usually the Ka is going to be the value that's provided for me. So I don't have to go through kind of that round the block stuff to be like, okay, I wrote a base equation, so I need to use a Kb. I wrote a base equation, so I'm going to have X equal to OH minus. So then I've got 2 steps to get pH. So you could do it that way and it wouldn't be wrong. There's just going to be a few more steps that we'd have to make sure that we do carefully. But going through our ice table, okay, solving for X, and I know this is a lot that's on here. So here's our ice table. Coming up here is how we're going to solve for X. X is going to be equal to this value right down here. And then this tells us that our pH after we take the negative log of X, which is our H3O plus concentration, is going to be 3.78. So let me box here. This is the solution for the problem if we were to do an ice table, everything that's written there. Totally a valid way to do it. But if we know that we have a buffer, another option that's available to us is to use the Henderson-Hasselbalch equation. Look at how much simpler that is from a calculation standpoint. You don't need to memorize the Henderson-Hasselbalch equation. It'll be provided for you. But 2 things we need to be very careful of. We cannot use the Henderson-Hasselbalch equation if either of these values is 0. If we don't have a weak acid and its conjugate base, or a weak base and its conjugate acid. You have to have both of those. And we have to make sure that we put them in the right spots. And we discussed in class that have a prediction, right, beforehand. What do you think this pH should be, right? Now, we figured out before that our pKa was going to be 3.76 when we started with that buffer. Now that we're adding some base, it should be higher. And it's going to be higher. But if you got something that was lower, that probably meant that you switched those 2 values. So kind of have that logic hat on and make sure that your number makes sense, because it's easy with these kinds of problems to kind of make some mistakes and switch your pieces. So I'm going to pause there for a second, because that's sort of the walkthrough for the solution. And Abigail, since you're here in person, you get an opportunity to ask any questions in person if you had any on this problem.
I don't think I have any questions on this problem specifically, so.
Okay, good. There's a lot to these problems, but I hope what people are seeing as you've been with me on this journey since learning unit 6 on equilibria, like we've been building to this. We learned how to do ice tables, and then we learned about acids and bases, and now we're doing chemistry with acids and bases. then doing equilibria. So we're kind of mixing all of these things together. So are there other questions you have, Abigail, or do you want to just go through the solutions for some of the problems from the worksheet from Friday?
Yeah, actually for the worksheet,
Mhm.
the one that talks about the one that required the quadratic equation,
Oh, yep.
it was more of the, I'm pretty sure it was that problem. I have to double check, but how did you know which KA value to use? Because when I looked on the appendix C, it was like the KA3.
Oh, yeah. Okay, good. Very good question. So since you asked this question on this problem, just in case anybody else is struggling with this problem just from the get-go, I'm going to start kind of from a little bit behind at the beginning, just so that we can walk through a solution for this problem. This problem is challenging once you get to the fact that you have to use the quadratic equation, and it's related to the fact that the Ka value is what it is. So we're going to talk about that and get to your question in just a second. But just stepping back and walking through for people who might be starting this problem from the beginning and not really knowing what to do. So this says the use of sodium phosphate, include clarifying crude sugar, manufacturing paper, removing boiler scale, and washing concrete. One of the skills that people have to be able to recognize is this is unessential information for this problem. It's just a context that hopefully makes the problem a little bit more interesting and real. I could give you this exact same problem by just writing what I have in brackets. So that first sentence doesn't have anything to do with anything that's going to be, necessary to solve the problem. The meat of the problem is, what is the pH of a solution that contains 33 grams of sodium phosphate per liter? Okay. And then it says, what is the hydroxide concentration of this solution? So here's my plan. I don't know what the concentration of this solution is, but because they gave me the grams of sodium phosphate that I have, I can use the molecular weight. And some of these problems that are a little bit more involved, they're going to ask you to do some additional skills, some of those skills that maybe if I'm just testing on one scale, I'll give you the molecular weight, I'll give you other pieces. But once I figure out the molecular weight, I can figure out the moles. And because this is per liter, that number is actually going to be the same number as the molarity, but that'll allow me to calculate the molarity. Okay, now I'm going to know the concentration and molarity of this solution, but then I need to think about what's in this solution. Remember, our last learning unit was on acids, bases, and salts. So what we have here is a salt. So if I take this salt and I dissolve it in water, I'm going to get 3 sodium cations, which don't do anything because they're spectators. And then I get 1 phosphate anion. Okay. So one of the things that's interesting, and Abigail, this is going to get at your question about which pKa value to choose, is phosphate actually comes from a triprotic acid. Okay. So this came essentially from this acid, phosphoric acid, losing a proton 3 times. And let me actually write this in something that'll stay here. So we've got H3PO4 that will lose 1 proton and become H2PO4 minus. So I'm just going to kind of show this as losing 1 proton, but keep in mind, it just doesn't have a proton that floats out into space. It gives it to water and we generate H3O plus. This is going to be Ka1. That's the first acid or the first proton that leaves. And then we're going to have Ka2. We're going to have another proton that comes off and we're going to get HPO4 2 minus. And you'll probably see the pattern here. Ka3 is going to be losing that last proton and generating PO4 3 minus. You with me so far? Okay. So what we need to do, and this is different from the stuff that we just worked on because there's no chemistry happening with this guy. We're just asking what's the pH of this solution. So now that I know the salt that dissolved in water and generated the conjugate base of a weak acid, I already know and I'm predicting that I'm going to make my solution basic. So that means I want to write an equilibrium expression that shows the guy that's in solution kind of doing a base equilibrium equation. So that means HPO4 3 minus, when it encounters water, is going to grab a proton and generate HPO4 2 minus and then leave behind hydroxide. So are you okay with that equilibrium equation? Okay, so now to get at the meat of your question, I have to figure out what's the equilibrium constant that I want to use for this. This is going to be a KB value, right? Because I wrote a base equation. With me so far? So here's the pieces that will go in my KB expression, but I need to use the Ka for the conjugate acid of the species that I wrote in my equation. I'm going to say that again because that's important. I need to use the Ka for the weak acid that appears as the conjugate acid in my equilibrium equation. Okay. And looking at what we have here, HPO4 2 minus going to PO4 3 minus, that's the weak acid. That's the conjugate acid that I have here. So I need to use the Ka value for that guy losing its proton as my Ka to convert to Kb. And that's why I use Ka3. That was a lot there, but did that make sense? Okay. And you can just give me thumbs up too. You don't have to worry about unmuting. So moving forward with how we work through the solution for this, okay? Now I know my ice table gets propagated, so my concentration is 0.2 molar. Here's the calculation for that, 33 grams of sodium phosphate. Here's the molecular weight, 163.94. Molarity is going to be 0.2013 moles divided by a liter, and I have 0.20 moles. So one of the things you can consider doing too, if you want, I didn't for this just to keep my page a little bit cleaner. I would probably keep more significant figures to that number as I go through my calculations, but just to make things a little bit simpler here, I just kept 2 significant figures with that because there's only 2 significant figures that I have here. So keep in mind that could be a reason too sometimes why people get slightly different answers than I might when we work through calculations. It depends on when and how you round, but that's usually why, especially if it's a Blackboard question, I'll give you plus or minus 5% so that it kind of allows for that wiggle room. Knowing that I need to have a Ka value, I use the Ka value, Ka3, which is actually the smallest Ka value. Now see if this makes sense. It's the smallest Ka value out of all of these, which means that last proton, taking off that last proton is actually the hardest one to take off because it's the weakest acid. Does that make sense? But because this is such a super weak acid, it actually makes the Kb value fairly large, okay? This guy really likes to grab a proton and go back and become HPO4 2 minus. Now, this is where this becomes a problem from our equilibrium standpoint, because if we think about that chemistry happening, here's the pile of PO4 3 minus that I have, and I just told you a lot of it wants to go back and be HPO4 2 minus. So that means my X is not going to be something super small. And I can figure that out kind of doing my pre-check. Remember, your pre-check takes the size of your pile and divides it by your K value. Okay, in this case, it's a Kb value because I'm looking at base chemistry. In this case, that number is not greater than 400, which means the size of the scoop that I'm going to be taking away is large. And so it's going to be very difficult to make an assumption here because my X is not going to be small. So at this point, highlighting, this is not the kind of problem you'd see on your test in terms of, I would not give you something that you needed to do the quadratic equation, but it's very possible that I could give you a problem just like this. You'd have to calculate the molarity, but it would be an equilibrium expression that's solvable using a simplifying assumption. So I'm going to pause for a second there and see if you had any other questions, because this was a problem you specifically asked to kind of think about.
Will there be any problems that require you to use like Ka2 or Ka3 as the Ka value?
Potentially. Now, the challenge with this one is because it was sodium phosphate like this, it was a problem. Now, see if this makes sense. If I gave you not sodium phosphate like that, but maybe if I gave you NaH2PO4, okay, then that's going to be looking at this equilibrium, okay? That's going to be a stronger acid, which means it might be a little bit smaller value for my Kb. So if I were to, I could make this exact same problem, except by choosing a different salt, I'm not choosing something that's all the way at the end, which is going to be a pretty strong base. I'm choosing something that's kind of in the middle so that the KB value is not going to be as large. And then you would be able to solve it using a simplifying assumption. Does that help?
Yeah.
Okay. In that case, just with this little example here, if I gave you this one, you would need to use Ka1 because when this salt dissolves, this is the piece, that's the conjugate base that I have in solution. So I'd need to use Ka1. Okay. Other questions on this? I'm just going to flip and show people how this quadratic gets solved. But again, I'm not going to give you a quadratic to solve on an exam. It just takes too much time. So again, you would not be asked to complete this problem after this phase, but maybe to this phase, I might say, you know, if you had a problem like this, that you couldn't make a simplifying assumption, I might say solve to the portion where you're, you know, you need to solve for X or something. But going through this guy, what you basically have to do is I have to multiply both sides by 0.2 minus X, and then I push this through algebraically. So that's how I get this portion on the left and then X squared on the right. I combine all my terms and set it equal to 0. This is how you solve the quadratic equation. A, B, and C just represents coefficients that are in front of your X squared, your X, and then this is your constant term. And then you put it into this equation. Or one of the things I want to highlight to everybody, if you haven't looked and found these yet, actually, let me see if I think I can be able to go here and show you some things. I can do it on my iPad here. If you haven't gone to this resources tab that we have here on Blackboard, a couple of things that I utilize all the time. And if you're working through problems where you kind of want to get to do something kind of a little bit more quickly, I'm assuming you guys know how to solve for molecular weight. But the first thing that we have on top of this page here is we've got a molecular weight calculator. So that's kind of a neat thing. If you haven't been to this website yet, I'll just kind of show you. You literally just type in down here, you know, your molecular formula, and it'll calculate your molecular weight. So a super easy way to kind of get to molecular weights when you're just kind of working through problems. And then there's also a quadratic equation solver. So clicking on this tab will get you to a place where you basically just put in your A, your B, and your X values, and it will give you your two answers. Okay. So one of the things to highlight here is you're always going to have, oops, so I put in a 0 there. I didn't mean for it to do that. Let's kind of delete that. So when you have this, come on. When you have this, you'll notice you always get two answers. One of your answers will either be negative and obviously not right, or it will be of a value that doesn't make sense. Because remember, this is what our X is. So if this number ends up being larger than you're trying to subtract it off of, you know you can eliminate that answer. So I do want you to be able to think about kind of this quadratic equation piece. On your semester exams, it's not something that you're going to see. But, you know, there's potential on your final exam. You are going to have challenge questions, you know, that you're going to be able to pick one from. So if you know how to use the quadratic equation, now you'd have to do it by hand. You wouldn't be able to use like this quadratic equation solver. But, you know, there could be a problem where you might need to do that on the final exam because we have more time for something like that. All right, so let me come back here and Abigail, see if you have any other questions on this problem.
No, I think it was just the Ka thing that I was confused about. So
good. Any other questions on the problems that we went through kind of practicing here?
I don't think so. I'm sure that afterwards I'm going to think of something, but I'll just email you if I have a question about it.
That's fine. What I'm going to do right now, and you're welcome to stick around or you're absolutely free to leave. I'm just going to run through, since you're the only one here, you're welcome to leave, but I'm just going to record sort of audio for kind of walking through these problems for people who maybe still were struggling and didn't get the right answer, so that when I post this, it'll have that. So whatever you want to do, no pressure. If you wanted to just kind of take off because you know that you're good, I'm totally fine with that.
So you're saying you're just gonna go through the problems we did on the worksheet on Friday and just like go through.
I'm just
Actually,
gonna-
now that I'm here, I think I do remember a question I had for this problem specifically. So I understand the logic behind finding the H3O plus concentrations for 4.52 and 5.25 and then finding the difference.
Mhm.
But I was trying to do it in such a way where I took the 5.25 and subtracted the 4.52, and I tried to take the 10 to that answer, but for some reason I wasn't getting the same number, and I honestly not understanding why.
I'm going to have to think about that. That's a good question because I want to walk through, and in theory, it sounds like you should be able to get the right answer. Like the delta pH should still be able to give you the delta hydroxide concentration. So I'm going to work through that offline, and I'll circle back and let you know. But I think that still should work. So I'm going to have to kind of check out the math for it, and I'll kind of send you a worked out solution if that's the case, but it should work. It should work. All right. So again, you're welcome to stick around, but I'm totally fine. I know people have a lot of busy things going on in their schedule. It's only going to take me a few minutes here. I'm just going to run through and kind of walk through the solutions for each of these in case people kind of need a little bit of explanation, but it sounds like you worked through all of them. And with the exception of that one question that you just asked me, it sounds like you're good with the solutions.
I think I'll stick around because it usually makes more sense to me if I have someone actually explaining the steps behind it, even if I did the math already.
Totally fine. All right. So I'm just going to go through. I'll pause after each one. I'll see if you have questions on it. And then that'll be what I'll wrap up with for tonight here. So, and many people, and you know what, in hindsight, I probably should have put a different problem first. This is a little bit challenging of a problem in terms of it's a little bit out of the box in terms of it's not the what's the pH of this solution problem that people have kind of been thinking about and planning for their quiz. So, you know, I did want to put some problems on this practice sheet that allowed people to use their skills and problem solve in a different way. But I felt bad because I think some people started this and they're like, I can't even get the first problem. Like, this is really challenging. And then there were some other ones that came a little bit later on, which were a little bit more typical of what we had been working on. So in future, I might move this one a little bit later so people don't get discouraged early on feeling like I don't know what I'm doing. So, but this problem, you know, one of the things I want you to be able to do, you as a general you, is use the skills that you've learned about in potentially a different way. So these kind of problems sort of represent thinking outside of the box and problem solving using pieces of information that you've used in another way, but this is kind of in a different context. So in this case, we're changing the pH of the solution. We know we want to make it more basic. So that's sort of the first thing is we know that we need to be adding hydroxide to it because the first problem says how many, or first part says how many moles of H3O plus or OH minus must you add? Since we're increasing the pH, we know that we need to be adding hydroxide. And so we want to change the pH here. And so one of the things to remember is that pH is sort of concentration in disguise because I can use this equation to take a pH value and convert it into a concentration of hydronium ion, H3O plus. So I do that with both pHs and I get what I need to change the concentration of. And sometimes it's a little bit weird for people to think about subtracting concentrations, but see if this makes sense. I could convert each of these concentrations to number of moles by using my 5.6 liters. But I'm still going to end up with kind of the same number that I'm subtracting. And once I divide again by 5.6, so you can actually subtract concentrations. I know that was a little bit maybe of a thing that students were like, can I really do this? Can I subtract? I know I can subtract moles, but can I subtract concentrations? But think about what we do in an ICE table. We subtract concentrations. So that's okay to do. So the difference here represents the amount of H3O plus that's going to be converted to OH minus. So one of the things to remember, and I know I mentioned this to a few people as I was kind of walking around, KW is equal to H3O plus concentration times OH minus concentration. That's always equal to 10 to the minus 14th. So we've got this inverse relationship between H3O plus concentration and then OH minus concentration. So in this case, if I know my pH is increasing, conceptually, I know H3O plus is decreasing, but I must have that kind of companion increase in OH minus. So whatever we go down in H3O plus, we're going to have to go up in the corresponding OH minus. So that's how we're able to sort of make this assumption that whatever this delta concentration is, this represents the change in concentration. So I know that the change in OH minus concentration, and I kept significant figures here, is 2.45 and change times 10 to the minus fifth. Now, this is asking how many moles. This is an absolute amount. And one of those things I want you to kind of be able to think about is number of moles is an absolute amount. Concentration is a relative amount because it's contextualized per 1 liter. This is the number of moles I'd need to add if I had 1 liter of solution. Since I've got 5.6 liters of solution, I need to scale it up. So that's why in unit conversion will set me up to kind of recognize that if this is the concentration change or the number of moles that I have to add of OH minus, if I had 1 liter, hopefully it makes sense that I'm multiplying here by 5.6 liters. When I was circulating around, I saw sometimes people were dividing, not quite sure whether to multiply or divide. Always rely on unit conversion to be that piece that allows you to know whether you're multiplying or dividing. Because I can see for my units to cancel here, I'd have to multiply by 5.6 liters. So that tells me the number of moles of OH minus. Now that I'd have to have that I scaled it up for having 5.6 liters of solution, and rounding it to 2 significant figures, I get 1.4 times 10 to the minus fourth. So questions on that, Abigail?
No, I don't think so.
Okay, all right, moving on to the next problem here. This one was a little bit easier to sort of think about. I probably should have had this one be the number 1 on there so that people didn't get a little bit, like I said, discouraged, not feeling like they could work on the first problem that we had here. But, and one of the things you'll see as we move on in Gen Chem 2, I always like to draw pictures, especially as we get to more complicated problems, because it can sometimes help you figure out what's going on. So we've got a solution here that we want it to be pH 4, and we know that it is HF. We know that that's the weak acid that's in there. So they give us the Ka value for HF, and if we want to have a pH 4 solution, remember that actually tells me what the H3O plus concentration is, or by doing a math calculation, I can convert that pH into a concentration of H3O plus. Now, what was unique about this problem, and maybe you didn't see it right away, is we're actually working an ICE table backwards. So if we know that we've got HF, and this is why I encourage people, like, just start writing down stuff that you know, start kind of going through our kind of the steps that we know. It's like, all right, who's in solution and what's happening, and write an ICE table, especially if you know you've got things that are participating in equilibrium. So here we're going to have HF dissociating into H plus and F minus. But as I start trying to put in my ICEs, looking at this problem, it's like, well, wait a minute, I don't know what the concentration is. It's asking me to calculate the concentration. So that actually is my unknown. But pieces of information that are provided is it did tell me what the pH is. The pH mathematically can give me the equilibrium concentration of H plus. So that's how I get that piece down here. And remember, ICE tables are able to be sort of propagated and filled out because we can employ relationships between species. So for example, if I know what the H plus concentration is in this solution, by the fact that this is going to be the same coefficient in front of this, it's going to be the same value for that. Those were both X's, right? So that allows me to propagate this guy. And this also then allows me to propagate my change row, because if I assume that I didn't have any of these to start with, now I know what my change row is. It's going to be plus that value. And it means it's going to be minus that value from the HF that was dissociating. Here again is the X in my table. So this is what makes this problem different, is we've got X in a different spot. X is going to be not at the end in the equilibrium spot. X is in the initial spot. That's totally fine, right? all of these problems that we did in this on this worksheet, we're kind of thinking about doing something a little bit different than the typical way that we've done them. Problem solving using skills we know, but in a different context. So I still need to solve for X, but let's use our equilibrium expression for that. So they give me the Ka value, and now these are going to be the pieces that go in here. But notice this is not my X. My X is over here. Now I don't need, when I know when people were working through this problem, they're like, okay, make simplifying assumption. But we don't need to have a simplifying assumption here. Simplifying assumptions are required when we have X squared, X, and constants. I don't have X squared terms here. I only have X terms. So it's pretty easy to go and just solve this algebraically. Now I need to multiply both sides by X minus 10 to the minus fourth. So that gets propagated through here. So that's why I've got these values, 6.8 times 10 to the minus fourth X, minus 6.8 times 10 to the minus eighth. Multiplying these two together, algebraically, I get to this kind of scenario here, solving for X. And I know for some people, the algebra is becoming a little bit of an Achilles heel. You know how to do the chemistry, but we need to make sure you're practicing enough so that this algebra isn't sort of what limits you. Solving for X gives me 1.147 times 10 to the minus fourth, remembering that this X now represents my initial concentration of HF. So putting this now with the correct number of significant digits, I'm going to have 4 here because the pH of my solution, that's a measured value, had 3 significant figures, 1.15 times 10 to the minus fourth. Any questions, Abigail?
Nope, I'm good.
All right. Next problem. Okay. And again, each of these problems is one that asks us to take something that we learned about and sort of think about it in a different way. Okay. So we've got a 0.1 molar solution of acetic acid, and they tell us how much is dissociated. And now we want to know what the Ka value is. So we did a problem like this in class where we maybe said a 0.1 molar solution of acetic acid has a pH of blah, blah, blah. That was a way of telling us what our X was, because pH is going to be able to give us H plus concentration. Once we know H plus concentration, that tells us what our X is. This is just another way of doing that, because when we say that an acid is 1.3% dissociated, again, that's a way of saying what X is. So if X is equal to, again, our concentrations of these two species, if we take what our initial if we take what our initial concentration was and we multiply it by that percent dissociation says that 1.3% of means multiply, my initial concentration broke apart, dissociated. So that's how you can use your percent dissociation to get to an X value. Okay, so that was sort of the twist in this problem, is percent dissociation is another way of telling you what X is. Now that I know what X is, remember this problem was one of those type 1 problems. It's really asking us to calculate the Ka value. Most of the problems that we're going to do, we actually determine what the Ka value is. In this case, we determine what the equilibrium concentrations are using a provided Ka value. So for this problem, we basically need to know what these equilibrium concentrations are. So now that I know what my X is, I can take 0.1 minus that X to get my concentration of HAC. So that's the amount that has dissociated. Here is the X value. Again, we got that from the percent dissociation. And I put all of these pieces into my equilibrium expression and solve for my Ka value. Okay, questions on this guy?
When I subtracted 0.1 minus the 1.3 times 10 negative third, I got 0.0987 without like the extra 9 in it.
Oh, maybe. Okay. So I think, and thank you for pointing that out. When I remember, this was a problem that I was off by a factor of 10 in my answer. And the reason is because in my problem I didn't have a 0 here. I had 0.9. And maybe I just assumed that I was off by a factor of 10 there, but maybe it was 0.0987 and not 99. Maybe one of my 9s was a 0. So you're saying, and let me correct this here, that this should have been 0.0987.
At least that's what I got when I subtracted the two.
No, it's probably right. And I think this was a translating something wrong from my paper when I made this key to go over. And my initial misstep was I put 0.987. And then when I tried to correct it, I somehow put in another 9. Okay. So, and that might change this answer a little bit, but the premise of this is the same. So what do you get? Actually, I'm going to ask you. So this is 0.0987. So what do you get mathematically for an answer here? Do you still get 1.69 or probably
get 1.71. It was only slightly different.
You brought this up to me in class, I think, because you're like, I'm at 1.71, you're at 1.69. I'm like, oh, it's probably a rounding error. No, not a rounding error. It's probably me having an extra 9 in their error. So this is going to be 1.71. So in all honesty, that probably is going to be something that plus or minus 5% would fall within the correct answer anyway. But thank you for pointing that out, because you are right. It should be 0.987 and not 0.9987. All right. Thank you for bringing that up. Any other questions on this problem?
Nope, I think I'm good.
All right. So this was probably the problem I should have started with, because I think this problem was most typical of kind of the things that we've been doing. So I'm going to go through this one kind of quickly. We've got nitrous acid. We know that that's a weak acid. Remember, nitric acid, HNO3, having that extra oxygen, that's going to be a strong acid. So when we don't have as many oxygens, that's a clue that that's a weak acid. They give us the Ka value, and it's basically asking us if we've got a 0.6 molar solution, what are the concentrations of H3O plus, NO2 minus, and OH minus? So I know that this is a weak acid, so I'm going to write an acid dissociation equilibrium. I'm going to write a Ka expression, make my ice table. I know my initial concentration is 0.6. I have none of my other stuff, so my equilibrium shifts to the right with minus and plus x's. I go ahead and I put my pieces in here. I'm going to make a simplifying assumption so that I can make my algebra easier. X is equal to 0.02 and change. Okay, and this problem isn't asking us for the pH, so I don't actually have to do anything with negative log. I know a couple of people were like, I can't get the right answers that you have, because they were actually trying to do H3O plus, NO2 minus, and then they were trying to get this concentration as well. But the problem actually isn't asking you for HNO2 concentration, it's asking for hydroxide. So the first piece is a little bit easy, because H3O plus and NO2 minus are both X's. So they're both going to be rounded to significant figures, 2.1 times 10 to the minus 2. So they're going to be my X value. We need to do a little bit of calculating to figure out what hydroxide is, knowing that the relationship between hydroxide and hydronium is that multiplied together, they equal Kw. So I can convert hydronium ion concentration to hydroxide by taking Kw, 10 to the minus 14th, and dividing by H3O plus. Okay, in this case, my OH minus concentration is going to be 4.8 times 10 to the minus 13th. Okay. Questions? So a couple of things just to point out here. Always make sure that you're very clearly looking for what is the question prompt asking, because that's how I can make problems unique or different, is I can ask for different things. I can ask for POH and not pH. And I think, Abigail, you asked a great question in class one time. You're like, do people use POH? No, people usually use pH, but it's just one of those things that we learn and we think about. So be careful that if I ask for POH, you make sure to kind of provide that right answer. But this one was pretty straightforward. This one probably was most similar to the things that we've been plugging and chugging along and doing. Any questions on this one? Nope. All right. This is another problem that uses this percent dissociation. So remember, if you see percent dissociation, that's telling you your X value. Now, it doesn't tell you your X value directly. Okay, so 0.03, which is the percentage, is not your dissociation. We're saying that 0.3% of, so multiplied by our concentration, dissociates. So that's how you get your X value, is it's the percentage as a decimal, right? So 3% dissociated is 0.03. We need to multiply it by our initial concentration, and that gives us our X value. So just like we did in our last problem, in this case, we're calculating these kind of pieces here. So we can set up an ICE table. That ICE table is going to allow us to calculate HA concentration, okay, which we don't necessarily need for this problem, but it's 0.194 molar because it's going to be 0.2 minus X. The problem does ask us to calculate H plus H3O plus concentration. That is our X. And then we can do round the block calculations to get the rest of those pieces. So our X is essentially equal to the H3O plus concentration. So that is going to be the first piece that we need. Negative log of that gives us our pH. Now going around the block, I can take that H3O plus concentration and convert it to OH minus using my relationship with KW. So that's how I get the concentration of OH minus. Taking the negative log of that can get me to the POH, which is 11.8, but just highlighting, I could also take 14 minus the, this should say pH. That's a mistake on my part. Let me go ahead and fix that. 14 minus the pH is going to be what gives us the POH, which is also 11.8. Good with that part? Now the next part kind of builds on it. And it's like, okay, go ahead and calculate the Ka of the acid, which is why we needed this piece, because the Ka is going to be H plus times A minus over HA. So H plus and A minus are both my X values. So that's why I see that there twice. And this value was necessary to put in my denominator here to calculate my Ka. Propagating it to two significant figures gives me 1.9 times 10 to the minus fourth. Good. All right. And we actually went through this problem, so I'm not going to go through this one again because we talked about that solution. Last problem here. And the key with this one is this is basically just like a lot of problems that we've done. So don't be scary if it's a biological molecule or it's a bigger molecule. That's one of the things I want to get across to people who are, especially, we got a lot of biology majors who have to take general chemistry. Applying the basic chemistry principles to larger molecules generally just is seeing that pattern and recognizing what you need to do. So sodium stearate is actually a fatty acid salt. So when we have fat molecules that are in your body, they're fatty acids, and they have this carboxylic acid group at the end, that COOH. So when we have it as a salt, it basically is the conjugate base of that weak acid, that carboxylic acid. So one of the things that you need to be able to recognize is, oh, that's a salt because I see the sodium there. But that's just like a really, really big, conjugate base piece. Okay. So one of the things that I did for this problem to kind of make it a little bit simpler to think about is I just labeled the rest of this R, like that's the rest of the molecule. It's not doing anything with chemistry or acid-base stuff. So I really don't even need to think about it. I needed to know what it was to calculate the molecular weight, because this is another problem where they give me a mass of something. So to get to molarity, I need to know what the molecular weight is. But see if you can follow this logic here. Here I have a carboxylic acid, that's the salt. So I've got the conjugate base and as a salt. So when I dissolve this in water, the sodium is going to be a spectator ion. And then I've got this guy left. I need you guys to be able to recognize that when you see a COO minus, that's how that actually looks like. I know maybe this is one of those things that I kind of made a leap. We talked about this when we did structures of molecules, but maybe that was a little bit of a leap that everybody knows that COO really looks like this when we kind of write it out as a Lewis structure. But I want you to recognize that that is the conjugate base of a weak acid, a carboxylic acid. We talked about carboxylic acids today. If I had had a hydrogen there, that would be a carboxylic acid. So because that hydrogen isn't there, it's the conjugate base of a weak acid. Okay, so now I know that I've got the conjugate base of a weak acid in solution. Okay, this is asking pH, so already my logic hat is on and I'm saying I should get a pH that's greater than 7. Okay, so let's kind of go through and work through what we need to do. This problem is exactly the same as we've done with other things, right? I'm going to write an ICE table. Okay, my chemical equation has to be relevant to who's in solution. I've got the conjugate base in solution. So that's what I need to start with over here. When that conjugate base encounters water, it takes a proton from water to regenerate the carboxylic acid and leave behind hydroxide. Because I wrote a base equilibrium, I have to use a Kb value. Now, notice this problem gave me a Ka value of what we call stearic acid. That's that guy. So I need to do the Kb, Kw sort of interconversion so that I can get what that Kb value is. So this problem is just like all the salt problems that we did. It just happens to be a bigger molecule as a salt. That negative, that anion part of our salt is not chloride or something like that. It's a pretty large biological molecule. That's our anion, but that's okay. Okay. Now, one other thing that's a little bit more involved with this problem is it tells me that I've got 0.42 grams of this salt that I dissolve in 10 milliliters. So I need to figure out what that molarity is, because that molarity is what goes here. So I need to take the mass that was given and figure out the molecular weight so I can convert that to moles. I put this all together in this part rather than keeping it separate, and then I divide by the volume that it's contained in. 10 milliliters is 0.01 moles. So there was a lot that I kind of simplified here to figure out what the molarity is, but the molarity is 0.137 molar. So that's what goes here in my ICE table. And now it's just solving these like we've done for all of our other problems. Okay, we're losing some of this and gaining some of this. I'm going to use a Kb expression that I make an assumption to be able to more easily solve for X. In this case, I have to remember that X is giving me hydroxide concentration. So negative log of that would be POH, but I should have, my logic hat on and say, stopping at 4.98 wouldn't be the right answer because I was expecting something greater than 7. So I'm going to subtract that from 14 and I get 9.01. Any questions on that one, Abigail?
I think I'm good.
Okay, so key takeaways from the kinds of things that we did in these problems is applying the skills that we've learned in different ways. So, part of being successful in general chemistry is not saying, I did this exact problem, Dr. Parenti is going to change numbers and just give me the N+1 version of it. There are certainly things like that that you'll see on the exam, but I wanted to give you guys more of an opportunity to practice some of those more like part 2 and part 3 type problems that you're going to see, which ask you to do a few more things and maybe pull in some skills from previous things that we've done. Maybe you're going to see a problem when it comes exam time that's going to be asking you to do some stoichiometry, right? The skill that we had to integrate from last exam was making sure that we knew how to use PV equals nRT. Both our kinetics and our equilibrium problem asked us to kind of bring that piece in. So you will have one of those challenge problems towards the end. You'll have, a number of options to pick from, but you're generally going to need to do a little bit more than just like the one-step skill problems. I think this was, that was the last problem that we had. So anything else, Abigail?
I don't really think so. At least the session helped answer like the big questions I had. So
good. And, one of the things I think, and you and I had this moment just the other day, sometimes students realize that there's like one little key thing that they are missing, or that's, excuse me, out of place, that allows them to kind of take a wrong turn on problems. And I'm just going to share, if you don't mind, what yours was, because I thought yours was great, that when you were kind of looking at this guy and you're like, okay, we drew these arrows and then we say that that's the acid, that's the weak acid, that's the conjugate acid of this guy. And that's a thought exercise to remind us that, oh, that's a conjugate base from a weak acid. So, okay, I'm going to have an equilibrium that I need to think about. There's acid base potential of this guy that we had here. But in doing that mental thought exercise, and you weren't the only person that did this, we started doing an equilibrium equation with that guy. But remember, we only can start equilibrium expressions and write equilibrium equations for things that are in solution. And what's in solution is the conjugate base, not the weak acid. Okay, so that was, and I always love when I see some things that students are doing, because it highlights maybe something that didn't get clarified well enough, either in a video or in lecture, for people to sort of understand that. So I love when I see that students have a little bit of a wrong turn, because it allows me then to make sure to share that out with the rest of the group. All right, well, perfect. We're only about an hour tonight, and I think we got a lot in that hopefully is going to help students kind of solidify their understanding of these topics. You good?
Yeah, I think so.
All right. Well, thanks for joining me tonight. All right, we'll see ya. Bye.